Last class we talked a little bit about slope fields, and we talked about how we can graph a differential equation's general solution, looking at a bunch of little line segments and how they made patterns. Today what we're going to do is talk about this method by this mathematician, and how do you say his name, do you think?
Euler.
It is Euler, that is correct. Most people pronounce it wrong. It looks like Euler, but it's Euler. It says right there, Euler. But anyway, it has to do, he was a very famous mathematician, did a lot of good things for mathematics. And what he was able to do is take what we did last class, which is I gave you a point and you kind of sketched in generally where the solution would be. This is a much more accurate way to find where the specific solution would be, even if you algebraically can't solve it, okay? Last class, we looked at a problem like number 1 right here. We actually did this one in class. dy dx is x minus y, and using the slope field, we were able to put together these line segments, and then we picked a point and we drew a general graph through this curve. But with Euler's method, if I gave you a point to start with, you could almost exactly get the curve, even though we mathematically, algebraically, cannot find the specific solution for this. We can't find the particular solution. Now, Euler's method is what is called an iterative process. Do you know what that word means? That may not be something you're familiar with. Iterative means you take your previous answer, put it into a process, and get a new answer. And then you put that into the same process and get an even better, closer answer. Yes?
Is that like finding the plus c?
It's not exactly like finding the plus c, because what you're doing is you're guessing here, and then you're making a better guess by moving over a little bit. Then you're making a better guess by moving over a little bit. So it's doing the same procedure over and over again until you get much more exact as to what you're finding. So what we do is we start with a point, the point where the process begins, okay? Your initial condition is what this is. And then using the slope, which is what the differential equation is, we go a little ways that slope, thank you, and go to the next dot. And then we do the same thing again. We calculate the slope at this dot and move down a little bit more. And then that gives us a much better estimate of where the curve goes. Has a lot of parallels with Riemann sums, okay? It says, and this explanation is a very good one. It says Euler's method is an iterative process. We start with a differential equation and possibly its slope field, and we're going to do one with a slope field, as well as an initial point. We plot the slope at that point and move to the next point by following the slope for a given distance, and that given distance is delta x, okay? So what we're basically doing is connecting a bunch of dots like a dot-to-dot puzzle, but the dot-to-dot actually goes the direction we need to go. This box right here explains very well the procedure. I want to point it out to you so that when you refer back to it later on and you're like, I don't remember where this table came from, you know what to do. You're given a differential equation and a given point, okay? You may not know the function, just know the diffie-q. You calculate the slope at the point you're given. For the given value of delta x, you calculate the delta y, the change in y, and that tells you how much to change your y value. The new value of x is the previous x plus delta x, and the new value of y is the previous y plus delta y. Now, in words, that may not make a whole lot of sense, but when we go through the process, it'll make a lot more sense, and it's a very simple process to do. Very calculator dependent for some of these problems. The first few, we really won't need the calculator. All right, let's consider this differential equation, dy dx equals x plus y, with the initial condition f of 0 is 3. We're going to use Euler's method to approximate f of 2. What's the y value going to be for 2 on the original equation, even if we don't know what the original equation is? So here's what we do. I want you to draw a table. You need 4 columns, so draw 3 vertical lines like this, and then 1 horizontal line across the top. So we need 4 columns on the paper. And this is the majority of your workspace. You're not going to need much else except the chart. The column headings are going to be the same every time. The first 2 columns are x and y. The third column is dy dx. And the fourth column is just dy. Now, there is a formula for dy, which if you look at it, it makes total sense. And I'm going to write it down here the first time we do this. It happens to be dy dx times delta x. Now, if you think about that for a minute, isn't dx and delta x the same thing?
Yes.
Yes, and so basically they cancel each other out. Okay? You've got to remember that delta x or dx tells you how much to change your x value. Delta y or dy tells you how much to change your y value. And that's how we do this process. Okay? The first point they give us, our initial condition is 0, 3, and that is the first x and y that we write down. They will always give you that. Okay? Now, before we go any farther, the most critical point that we're going to need at this point in the process is delta x. Now, delta x is found exactly the same way we did with Riemann sums. Does anybody happen to remember the formula for delta x with Riemann sums? B minus a over n. Okay? Now, in this instance, b is the x value where you're stopping, and a is the x value where you're starting, just like a Riemann sum. So what x value are we stopping at? 2, and we started at 0. So 2 minus 0 over, and how many steps did they say to take? 4. So delta x would be what? 1/2. I'm going to write it as 0.5 because we're going to use a calculator. So your x's should go down the x column every 0.5. So 0 is my first, and then 0.5, 1, 1.5, and 2. Told us to stop at 2. All right. Now we begin the process. We first calculate dy dx for this specific point. Now remember, here's the formula for dy dx. Just like we did when we plotted the little line segments last class. Dy dx is the x-coordinate plus the y-coordinate. So what is the x-coordinate plus the y-coordinate? 3. So put a 3 right there. Now, dy is what you just got for dy dx times the delta x value, which is 0.5. So this is 3 times 0.5, which is what? 1.5. Now, in the future, you do not have to show the math in the dy column. I'm writing it here, though, to help you remember what we're doing for future reference. Okay? Now, this value is not your new y. It is how much your y changes. So if my y was 3 and it goes up by 1.5, what's my new y? 4.5. Does that make sense? dy, remember, tells you how much your y changes. My y was 3. That tells me to change it by 1.5. So now my new y is 4.5. Repeat the process. Find your dy dx for this new point. So x plus y. What's 0.5 plus 4.5? 5. So put 5 in the next column. So now to find dy, we take what we just found, 5, times delta x, which is still 0.5 and always will be for this problem, and that is 2.5. Are you with me? So we take the 2.5, add it to the 4.5, we get 7. That's our next one. Okay? I'll do one more with you, and then you're going to finish it up. So what is dy dx with the new point? 8. And then over here, dy is that 8 times 0.5, which is 4. So my new y value for 1.5 is 11. Okay, finish the process until you get down to the 2 and stop. As soon as you find 2's y value, you're done. Yes, ma'am.
So you're taking your delta x from the last column and adding it to whatever you got from the last y?
I am taking my this is my dy. I'm taking this y, this dy, this change in y, and adding it to the y that was there.
Yeah.
So I'm changing y by 7, and I get 11.
4 plus 7 is 11.
Yes, ma'am.
Okay. And then how do you get the next column?
dy dx, here's the formula for dy dx up here.
Oh, x plus y.
Right.
Oh,
Okay? Okay, as soon as you get the y, stop. You don't have to get the other 2 columns because you're not going any farther. Did you all get 17.25 for your y?
Yes.
Yes. So the answer to this question is that f of 2 is 17.25. So even though I don't know what the equation is, the particular solution is, I can find a point down the road given my initial condition. Okay? This is as hard as it gets. All right? Do you have any questions at this point? Do you think you can do one of these charts yourself? I think so. Let's do number 2, but I want to together find delta x, because if delta x is wrong, it's going to mess everything up. So we have x, we have y, we have dy dx, and we have just dy. Now, you don't have to write the equation for dy. You can if you want to. Yes?
Do we not have to finish the chart?
That's as far as we have to go. We want to know what f of 2 is. So we want the y value for 2 and we stop. So 0, 4 is my first point. I know that. Always put that down right away. Okay? Where does my chart want to end? 1. So what is delta x? 1 minus 0 over what? Which is over 4, which is 0.25. So 0.25, 0.5, 0.75, and 1. Those are your chart values. You do the rest. How did I get the y values?
Yeah.
Okay. Once you find the first dy, you add it to the y that you already had. Because the next y value is y plus its change. Okay? When you're done, look at the screen, see if you got the same answer I got. This isn't very hard, is it?
No.
If you're done, turn it over on the back. Start looking at that problem at the top. Yeah, we are going to do this one. It looks scary, but it's really not. Just read through the problem. This is the first taste of the real-world examples of what differential equations are used for. Tomorrow and the next day are going to be even more of the application problems because they are everywhere. So if you read along with me here, it says, let capital T of T denote the room temperature in Fahrenheit of a cup of coffee at time t minutes. That's actually, now that I think about this, it's not the room temperature. Yeah, the room temperature of the cup of coffee's temperature. It's a little bit misleading. Room temperature is 70 degrees constantly, and the coffee is 190 when it comes out of the microwave. The coffee's temperature is described by a differential equation, d capital T of d time is equal to this function here. This is your differential equation, even though it's not dy dx. Complete the table using Euler's method for 10 minutes. Plot your result on the accompanying slope field. So somebody else went in and did a slope field for this. And we're going to show you how the dots are going to follow this beautifully. They're going to follow right along with the way it's going to look. Then we're going to go back and we're actually going to solve this differential equation because we can. We learned last week how to separate variables and solve equations. We're going to do that on notebook paper because there's not enough room on here to do it. And then we're going to put those actual values and show how close they are, because this is a way to estimate what's going on. Do y'all remember linearization? A little bit. Does the word sound familiar?
Yeah.
The pigs in the fence.
No, that was optimization.
Oh.
Linearization is finding a value really close to a point on a curve. We're doing it multiple times. That's what Euler's method is all about. Okay, so here is my equation right here. So we're going to use the calculator to let us do this faster, and I'm going to teach you a new thing your calculator can do that you may not be aware of. I want you to go to y equals and type in this equation, and the t is going to be an x. So we have negative 0.1 parentheses x minus 70. Not 71, 70. Okay? This is very handy when you need to plug in numbers multiple times, especially with an ugly equation like this one. Okay? After you're done, just push second quit. We're not going to graph it. We're not going to look at the table. We're going to do it very differently. All right? Now, What is delta x? They've already done your table for you. It's 1, isn't it? So the dy dt column and the dy column are going to be exactly the same because it's just multiplying by 1. So that's why there's not 4 columns here for this. They don't have, this actually should be d capital T over dt. Fix this one here. It should be d capital T over dt. We don't have a d capital T column because we don't need one. It's the same as this one. Okay, we're not going to just write it twice. So here's how this works. On your calculator, what we want to do now is we want to take this and we want to plug it into this equation to get the slope, right? That's the first step. But the slope is in my calculator. So what you're going to do is on the home screen, is everybody on the home screen? I want you to get a y1 right there. Do you remember how to do that? Alpha, trace, and enter. Put a y1 right there, put a parentheses, and put in the 190. That tells the calculator you want to plug 190 into that equation. Push enter. There's the answer, negative 12. And that goes in this column right there. Okay? Move it up just a little bit. Got a glare. You see that? Okay? So this is also my d capital T by itself. So I'm going to take my t, subtract the 12, and I can do that on the calculator. I get 178. That goes in, that's my new t value. Does everybody understand why I don't have my 4th column yet? I don't think you do. Question?
Wait, when you said subtract, I thought it would have been 202. I thought it was negative.
No, you actually usually add it on,
Oh, okay.
but this time we're subtracting because it's negative. DJ, question?
Is the reason we don't have the 4th column because we don't know what delta x is?
We do know what delta x is. It's 1.
Oh, yeah, right.
It's 1. Delta x is 1. So if we put in a 4th column that said just d capital T, it would be this value times 1 every time. So it's just recopying that column. So I don't mess with it. I don't have to write it again. Okay? So now I subtracted these two and I have 178. Now I want to plug 178 into the equation. Yes, sir?
So when you said that you'd just be multiplying it by 1 every time, is it because like there are 10 steps every 10 minutes?
Yes. Each x is 1 unit apart. That's why. Okay? So now I want to plug this into the equation. So here's what you do. Everybody look up here for just a minute. Go up twice, 4 times on your calculator. Just do up arrow 4 times. And then push enter. You have just now recaptured that line. Now just change the 190 to 178. Just type over it. Okay? And then push enter. So you don't have to go get that y1 again. So that's my new one here, negative 10.8. Now we subtract those two values. So 178 minus 10.8 equals 167.2. Now, for the rest of this paper, please round to the first decimal place. Don't go any farther than the 1 decimal place, all right? So do you think you can continue this?
Yeah.
Okay. So we just go back up there. For those who need another step with me, go back up, capture that y1, change the number. So that'd be negative 9.7. And then subtract those two.
Can we just round it to fit in the box?
Round it to 1 decimal place, yes. That way we all have the same numbers. Now this is a little tedious, I know. But if you don't have an equation, this is what you have to do. Those of you who are done, the others can catch up in a minute, I want you to plot those points on your graph that you just found. Get you started. So 0, 190, that's right on the y-axis, right up here at 190, okay? And then 1 is 178, so it's about right below 180. You see what I'm doing? 2 is 167. It's a little bit lower, and so on. So plot all those points that you just found. That dot up above the graph is wrong. You will end up, yes, go ahead and connect them. And if you notice, they follow the slope field pretty well, don't they? So go ahead and connect them with a smooth curve. None of the dots really, except for one, touched one of the arrows, does it? But they have the same general progression that the arrows do. So that is a very good estimate of where the particular solution would be if you started at 190. If I asked you to sketch it in, you probably do pretty close to this, but this is very close. And we're about to find out how close it actually is. Okay. Is anybody still plotting points? Okay, now please go to your notebook paper. And on the notebook paper, we need to copy down that differential equation. D capital T over D little t equals negative 0.1 parentheses capital T minus 70. We are going to review something we learned already. That is the separation of variables that we did last week. I'm actually going to solve this thing. Now, for those of you who still have not finished worksheet 1, the worksheet 2 on the separation of variables, I want to give you a hint that might help you out as far as things go. When you separate variables, if you have constants multiplied in the front, the best thing to do is leave them where they are. Okay? I'll be more specific in just a minute. Who remembers the first thing we do to solve this problem? Okay, so we need to separate the variables. So which dt should I move? You always move the bottom one. Always. Always. So mark out dt, little t, and move it over there. Okay. Now, the t minus 70 is 1 unit. It has to move together. So I need to divide it off, but the 0.1 can stay there, and it's best if it does. It's going to make the integrating much easier. So now I have dt over t minus 70 equals negative 0.1 d lowercase t. All these big t's and little t's get a little confusing. Okay. Are my variables now separated completely? Yes. What's the next step? Antiderivative. Integrate both sides. So draw your integral symbol on both sides. All right, I have a fraction. First question you ask yourself, is the top the derivative of the bottom? Yes. So what kind of integral will it be? It is ln. Very good. ln, absolute value of t minus 70 equals. Now this side tends to bother people because it's a weird decimal. Now, being a constant, I can just move it outside, can't I? So let's do that. Let's just move it out. What would be left in its place? Just dt, or you can say a 1 is there. So what's the integral of just a dt?
T.
Just a t. So we put a t on there, and don't forget your plus c. So I have found a general solution, but I'm going to keep going and solve it a little bit more because I have an initial condition to plug in. So to get the big T by itself, what do I need to do? Raise both sides to the power of e. So e parentheses, and then e parentheses to the other side. Remember that e and ln are inverses of each other, so they cancel each other out. So the left side is just t minus 70 without absolute values anymore. The other side, because the c is up in the power, I need to separate it. So it's going to be e to the negative 0.1t times e to the c. Do you remember this from last week? I think we did this on Wednesday. And this e to the c is just another big C. It goes in front of the e that's still there. So t minus 70 equals c e to the negative 0.1 t. Okay. To get the final answer, once I found c, I've got to move the 70. I don't have to move it yet. So I'm going to honestly leave it there. Otherwise, I'm going to have to move it back. I just know what's going to happen. Okay, look back on your worksheet, please, and see if you can find what the initial condition was. What was the first point they gave us for this problem?
190. 90 degrees. Times 0.
0, comma,
190.
190. The time was 0, the temperature was 190. That's how hot the coffee was when we took it out of the oven, or the microwave. Oven. Yeah, we put coffee in the oven. At my house we do. No. We don't have a microwave at my house. Seriously, we don't. No microwave at my house.
Why not? How do you make
David
ramen
cooks
noodles?
everything by hand.
Oh my god, that was so good, bro.
What's happening with that? She's recording.
No, I didn't hear what you said, and it's being cut out of the video anyway. No,
I said he used super bread.
oh.
Don't laugh.
Okay, here we go. Woo! I'm going like this to tell me when to stop cutting. All right, so now we plug in the values. The 190 is big T minus 70 equals C e to the negative 0.1 times 0. So little t is 0, big T is 190. So we plug in the values and we solve for C. So 190 minus 70 is 120. And what's going to happen to the E term? It equals 1 because it's CE to the 0, which is 1. So C times 1, which is just C, equals 120. So there I have found my C value. So my equations now says T minus 70 equals 120 e to the negative 0.1 t. And now I want to get big T by itself because I'm going to plug it in the calculator. So big T equals 120 e to the negative 0.1 t plus 70. That is the actual particular solution for this differential equation. And now we're going to see how close these y values are to the ones that we calculated using Euler's method. So before we cover this up, take your calculator, go back to y equals and type that equation into y equals instead. 120 e to the negative 0.1 x, down, right arrow to come down, plus 70. I'm off the screen. There we go. Now this is going to go much faster than the Eulers did because we're just reading values off of a chart. Okay? So if you have your second color and want to use it, this is where it will come in handy. I'm going to go back to my worksheet. And now I want to read the values off of the table when t is 0 through 10. So second and table. Scroll to where 0 is your first value and start copying those down, rounding to 1 decimal place in the far right-hand column. So 0 is 190. Those are the same, of course. The next one is 178.6, which is pretty close to the 178 I calculated, and so on. So just go ahead and copy those down real quick. Once you're done copying those values off the table, plot those points on the same graph in your new color and see how close they are to the original points. So as you can see, they're pretty darn close to the real graph. So in some instances, if we can find the differential equation, it's just faster to do that, to go through the math that we did, plug in the values we want. But if you can't find the differential equation's particular solution quickly, this is a method that works very well to give you a good estimate of what you need. Yes, sir?
Why does the gap seem to progressively get bigger? Like
Because of the space between our guesses, we did them one minute apart. That's quite a big gap. If we had done them closer together, say every 30 seconds, it wouldn't have been quite so drastic of a change. But once one of them gets off by some, it throws everything else off from that point forward. Does anyone else have a question? It's a pretty simple process. Do you agree with me? And that problem was scary, but it wasn't so bad. Now, if I asked you questions such as, coffee is cool enough to drink when it's below 120 degrees, after how long will it be at that temperature? Somewhere between 8 and 9 minutes. Do you agree with that? That's kind of important things to know. Nobody not likes burning their tongue on hot coffee, do they? No. I hope not. Then, yeah, cold coffee is not good either. Okay, so that is the most difficult these questions do get, but they do get a little bit more unique. And I will tell you this, on the AP exam, there will not be any sort of, well, should I use Euler's method or not? They will come right out and tell you. Use Euler's method with this many steps to do this. As long as you remember what Euler's method is, you're good to go.
So you don't have to write it out to the side like you do locus levels?
No, you do not, because they will let you know. All right, so let's look at one more quick question. And it says to determine the approximate location of the relative minimum. We haven't talked about minimums today. For the function whose differential equation is given by this, Euler's method with a step of 0.25 is used. If the initial value is 0,4, on what interval does the relative minimum lie? Okay? So, we have to answer a relative, notice they embed the words Euler's method into the problem, so we have to use Euler's method. What happens on a graph when you have a minimum? What's the graph doing? It is decreasing, and then it changes to increasing. Now that's what F does. What is F prime doing?
Going from above the graph.
It's going from negative to positive. Do you agree with that statement? Does our chart give us the slope? When we do an Euler's method chart, do we get the slope? Yes, we do. We get the slope. So what we're going to be doing is we're going to be doing a chart, and it's not telling us when to stop as far as how many x's to go. It's saying stop when the slopes change from negative to positive. That's where the min's going to be. Okay, so write yourself a note out to the side that says find where dy dx changes from negative to positive. So that's what we're going to do. We're going to start a process. We're going to start an Euler's method chart, and we're going to go until the slope changes from negative to positive, and then we're going to stop. So I'm going to change back to my other color, just because I like it better. Build my chart. X, y, dy dx, dy. Where does this problem tell us to start? What's our initial point?
0,4.
0,4. Does it tell us what delta x is?
Yes.
Yes, it does. What is it? 0.25. So I'm just going to go ahead and start writing some random x's down. I don't know how far I'm going to have to go. I'm going to go out to 1. I may not even have to go that far. Make sure they're spaced apart, 0.25. Now we start the process. I'm going to use my calculator because it helps me. So, dy dx this time is 2 times the x. Well, that's easy. That's 0. Minus 4 plus 2. Negative 2. Oh, let's write out to the side delta x equals 0.25. Because remember, we take our slope, we multiply it by that to put it in the dy column. So negative 2 times 0.25 is negative 0.5. Okay? Are we good with that? Okay. What is my new y value? Oh, I'm sorry. Question.
For our x, are we always just gonna go up to 1?
I'm going as far as I need to, as I might need to. I may have to go farther. I don't know yet. But I just started going by 0.25s. Okay? What is my new y value? 3.5. Very good. Okay, so now it is 2 times x, 2 times 0.25, minus the y, plus 2. I get negative 1. So the dy column is this answer times 0.25 which is negative 0.25. So what is my next y? 3.25? Are we right? So 2 times x, 0.5, minus 3.25 plus 2, negative 0.25. That's a small dy dx. But that makes sense because they're negative and they're getting closer to 0. We want it to change to positive. That's the whole point. So this times my that x, so times 0.25, is negative 0.0625. I add that to the 3.25 that's already there. And this is 3.1875. I'm being more accurate this time because I really want to see where it changes from negative to positive as quickly as possible. Okay, so once again, 2 times my x, 0.75, minus my y, plus 2. And there we go. Has my slope changed from negative to positive?
Yeah.
Yes, it has. I'm done. Stop. Don't go any farther. It's right there. So the question is worded on what interval does the relative minimum lie? So the relative minimum lies on the interval of what? 0.5 to 0.75. That's where it fell between, right? Because why?
The slope,
The
because
dy
the slope
dx
changes on the
change.
line.
Because dy dx, that's what we called it in the problem, changed from what to what?
Negative to positive.
Negative to positive. That's our reason. Do you have any questions about that problem? Same process, just looking for something different.